Hi, my name is Emma Snyder, and this is Lab 1, Charge Tape. The purpose of this lab is to demonstrate knowledge of a charged insulator. In this case, tape is charged and tested in a few different experiments. Then the tape is modeled by a computer as point charges, and the charge on them is calculated. This lab demonstrates the knowledge of electric fields and the forces that they cause, as well as how those forces relate with forces of other kinds, in this case, the gravitational force. The fundamental physics principle used in this lab, they're Newton's third law, that all objects act upon each other in opposite directions with equal force, and Coulomb's law, which can be read there. The end result of this lab is that the charge on the piece of tape was 0.504 coulombs and that the electric force on the floating tape was 0.0003135 newtons. The first important concept is Newton's third law, which states that every force causes another equal but opposite force. This is important when modeling the electric field because the force that acts on one piece of tape also is exerted on the other, and that is shown here. And then the next important concept is Coulomb's law, which describes the force acted on or exerted on one particle due to the electric charge, and the formula for that is shown below. I created a code that would model the way that the two pieces of tape would have interacted if they were point particles. Assumptions that were made: there is no air resistance on the tape. The tape is a point charge holding the full piece of the charge of the piece of tape. Each piece of tape has the same charge on it, and the model was used because it was an efficient way to show the electric force and to find the charge on the tape. And then the result is that the charge on each tape is 0.504 coulombs, and this right here is an image of the model. So, for the experiment, I created a charged piece of tape by pressing it firmly on top of another piece of tape and then ripping it off quickly. This charged the tape, which was then held close to another piece of tape that was charged using the same method. One was held horizontally and the other one was brought close from the bottom. The distance between the two, at which the top tape started levitating, was then measured. The system is the top tape, the surroundings are everything but including the bottom tape and the earth. The initial conditions are the top tape at rest, and it was charged with an unknown charge and gravity acting downwards upon it. The result was that the top tape levitates at 0.0003 meters, and the electric force is 0.0003136 newtons. So the length of the piece of tape was 0.32 meters, so the weight of it was 0.00032 kilograms. And then that means that the distance between the two tapes when it began to float was 0.0003 meters, and that the gravitational force was 0.0003136 newtons, which was also the magnitude of the electric force on the floating tape. So this right here is the code that I used for the model. It's pretty simple, but these are the constants, these are the objects that represent the 2-point particles of the tape. And then here is where I calculated the charge on them using the force and the position from the initial experiments. And then here I plotted the arrows to show you how the force is acting on each one, the electric force. And right here are the number of coulombs. So as far as coding went, like I said before, the magnitude of the charge on one piece of tape was 0.504 coulombs. And then as far as assumptions that we made for this code, it was that there was no air resistance on the moving object and that the long tape, it was a point charge with the charge concentrated in the center. However, we did not make this last assumption that was listed. So as far as the model versus the real life experiment, the similarities were that both represent gravity as a counteractive force and use the same math, and they required that the net force be zero. And then the differences were that the experiment had no way to guarantee that there was equal charge on the two pieces of tape, but the model assumed that. The experiment was trying to find the distance at which one tape repels the other, and the model was based on that and used its data to find the charge from the tapes, and then the model assumed that there was no air resistance, which did exist in the experiment. There were two major sources of error that could have possibly existed: an error in measuring the distance between the two tapes, and a charge on one tape being greater than the other. And then, as far as changing the charges of protons and electrons, that would not have made a difference in the way that the tape behaved when with other charged objects, because it would simply flip the charge of all objects, including those of other charged objects. So, for example, if the pen was initially positive and the tape was negative, and then you flipped protons and electrons, they would still attract because one would still be positive and one would still be negative, so they would still attract. And then touching the tapes too much would make it transfer into, like, make the charge transfer into the hands, causing the tape to lose its charge. And if the tape loses all of its charge, it won't behave the same way that it was previously. So in conclusion, in this experiment, we found that the two tapes repelled each other at 3 millimeters, and that the force on each one was 0.0003136 newtons. And these values were used to find the charge on the tape to be 0.504 coulombs. And here you can see the model one more time.